Howdy, howdy. So we're going to be moving on as a kind of a segue into a unit on bonding. So Unit 7 is about bonding. So we'll be tackling a little bit of the stuff we did with electrons and some of that kind of bridge unit with ionization energy and Bohr diagrams and atomic size. It's kind of bridging us over into bonding. All right, and the next piece that we're going to add here is kind of about valence electrons and what we call dot diagrams, electron or Lewis dot diagrams. All right, so what we're going to be doing first is being able to define valence electrons and also to determine the number of valence electrons based on electron configuration and position on the periodic table. And we'll also learn how to then use the valence electrons to make Lewis dot diagrams. I probably should have added that to my bulleted list here. So Lewis dot diagrams. Sorry about that. Okay, so those are our primary objectives. And it's been a short video, so I'm going to get after it real fast. All right, so first of all, valence electrons. So as you saw in Chem Quest number 15, you should have come across a definition for valence electrons as electrons that reside in the outermost or highest energy level. All right, and we'll talk about what that looks like with electron configurations, etc., in just a little bit. But if we look at selenium, so here is the completed electron configuration for selenium. So it's 34 electrons, and if you add up all my little superscripts here, that should come out to 34. Now, we have to be careful here. So when we talk about energy level, we're not talking about sublevel. We're talking the overall energy level itself, which is indicated by a number, not a letter. Okay, so the 1 indicates energy level 1. Those are energy level 2, energy level 3. So energy level 4 is our highest energy level. And if you look at energy level 4 in its entirety, we have 2 in that S sublevel that are a part of energy level 4, and 4 more there. So the number of valence electrons indicated by this electron configuration is 4 plus 2, or 6 valence electrons. So again, we're only concerned about those electrons that occupy the highest energy level, and the energy level is indicated by these numbers. So number 4 is the highest, so we do not count those 10 in energy level 3D. Okay? Now, the reason valence electrons are important to us is that those electrons are what determine chemical behavior. What do elements bond with? Are they a positive or negative ion? Do they form ions? How do they bond? What sort of molecular shape do they take on? That's all determined by these valence electrons. And we're going to learn how to use those to make bonding kind of three-dimensional here later. But for now, we just need to understand what they are and how we can figure out how many valence electrons we're dealing with. Okay? So selenium would have 6 valence electrons. These 2 plus those 4. Which are in the highest energy level. Right. Now, we can also figure out how many valence electrons we have just simply based on its position in the periodic table. So it's not, you don't have to have the electron configuration to figure this out. There's a way to tell. Just like I taught you how, this column's always a +1, this column's always a +2, etc. There's also a way to use the periodic table to figure out how many valence electrons you have, and it's really easy. All right. So group 1 has 1 valence electron. Group 2 has 2, and in fact, all of the D block also has 2 valence electrons. Okay, you're confused as to why that is. You have to remember that our D block is 1 energy level behind, right? So these, for example, will be our 4s, 1 and 2. These are all 3D, so those electrons in the 3D sublevel don't count. So 1, and then 2 all the way over, then it goes 3, 4, 5, 6, 7, and 8. Now I drew that little line there to indicate the fact that helium itself only has 2 valence electrons. So it's sort of the odd man out in that group of noble gases. Now it still belongs there because of its behavior, but it only has 2 electrons total, so it obviously can't have 8 valence electrons. All right, so that's how you can use your periodic table. And so I encourage you right now to maybe pause this and go to your periodic table that you have of your own and label that, maybe with a different color from the charges you wrote for the chemical formulas unit. All right, we still want those charges, but we also want to indicate number of valence electrons simply based on where it is on the periodic table. Okay, so now that we know how to do valence electrons and figure out how many we have, the next step is to draw Lewis dot structures, okay, or Lewis dot diagrams. And the way that we do that is actually really easy. It's like a simplified Bohr diagram. All right. So if you recall Bohr diagrams, they are concentric rings that show where electrons are. So a Lewis dot structure is similar, but actually much simpler. All right. So let's take lithium, for example. All right. So I'm going to go back a slide. Lithium's in this column with one valence electron. So all I'm going to do for lithium, its Lewis dot structure is the symbol Li, and then a single dot. Okay. If we did, let's pick maybe carbon. Okay, so carbon has 4 valence electrons. So I'm going to draw the symbol C, and then 1, 2, 3, 4 dots around it. Okay, to show those 4 valence electrons. Now, notice we're kind of doing something similar to Hund's rule in that, we can put up to 8 for 8 valence electrons. Notice we're never indicating more than 8 based on what I showed you on the periodic table. But we're going to have single electrons all the way around, 4 of them, before we go back and pair them up. All right. So notice that the 4 single electrons. So now let's go, back to let's go up to from carbon to oxygen, which has 6 valence electrons. Okay. So I'm going to do something very similar. I'm going to go with an O. I'm going to go 1, 2, 3, 4, 5, 6. All right. And so what oxygen is showing is 2 sets of paired electrons and then 2 single electrons. Now, you may be wondering at this point, does it matter whether I start over here or over here? No. What's important is that if there's 4 or less valence electrons, they're all singles. Okay. We do not pair them up until we've got 4 singles all the way around. Then we go back and pair up. And the maximum we show is 8. Okay. Now, the implications of this to bonding, etc., that'll kind of get built upon. For now, this is all I want us to master. So here we are, 8 minutes on the nose.